try to learn the fundamentals. I think there's this kind of trade-off. People want to, for example, take a course where they would use Fluent so that when they apply for jobs, they can say, I know Fluent, which makes sense. It's in the interest of ANSYS to make Fluent easy to learn because they have a nice GUI. It's not difficult to learn Fluent. Having time to learn finite element method and sit and play with that is much, much more difficult. It's even much more difficult when you're in academia. It's infinitely probably more difficult if you're in industry. So there are some things in life for which you only essentially have this time frame to do, and later it's not impossible, but it's difficult. So I would try to optimize working on those things when you are in that time frame.
Today I'll be talking with Timofey Mukha. Timofey is the chair of the Turbulence Technical Committee for OpenFOAM. He completed his PhD in scientific computing and is a postdoc at KAUST in Saudi Arabia. I hope you enjoy our conversation, and please like, subscribe, and hit the bell so you don't miss an episode. Thank you for joining today, Timofey. It's so good to have you.
Yes, it's my pleasure. Thank you so much for inviting me.
Absolutely. Can you give the audience a 1 to 2 minute intro of who you are and what you're working on?
Yeah, so to condense it, so right now, let's start from the current time. I'm at KAUST in Saudi Arabia, and I work as a postdoc with Matteo Parsani here. I work and have worked mainly on LES, quite a bit on wall-modeled LES in particular, although I also did a postdoc on what was essentially multi-phase flow in marine applications. So yeah, as I said, this is my third postdoc, and I was before at KTH in Stockholm in Sweden for my second postdoc. And going further back, I was at Chalmers on the west coast of Sweden for my first postdoc. And then I was on the east coast of Sweden in Uppsala, which is a little bit north of Stockholm, where I did my PhD, and essentially in wall-modeled LES at a department which is quite numerics focused, I would say. And previously I was on the west coast of Sweden. So as you can see, I was going around back and forth quite a bit to do my master, right, at Chalmers. So the same place where I did the first postdoc also. Yes, and that's the sort of a Swedish academic journey. And before that, I was in Russia, where I was, born and raised, where I did also a master and an undergrad in engineering physics at Bauman Moscow State University. So that about sums it up, I think, in a nutshell.
Yeah, that's awesome. Thanks for sharing. A couple questions on that. I didn't realize you traveled that much. What has been something that's been neat to you as you've gone to different places and in your experience, especially? Yeah, it just seems like you've had a lot of experience of.
Yeah, I would say the travel in Sweden doesn't bring too much surprises, nor does it, I suppose, within any given country. I mean, the system doesn't vary that much. Although it has been a little bit different sort of management styles on the higher sort of department level and so on. How much more corporate it was, or whether it was just completely loose academic style. But that was perhaps the only difference I would say within Sweden. Of course, moving from Russia to Sweden was especially, I was very young, right? 22. So, of course, that was a whole plethora of experiences and so on and so forth. In many ways, Sweden is completely, despises hierarchies, for example, which was new at university in particular. Now, again, moving country to Saudi, of course, also a lot of things are new, particularly the climate. But here we live sort of in our small little bubble at the university. It's about 8,000 people, I believe, in this big campus area here. And things are not so different here. And that's like in my immediate, so to speak, surroundings. I mean, it's extremely international. But yeah, of course, if you go outside, then things are different. And certainly things you don't see in Sweden. I mean, it's... everything starting from architecture to how the landscape looks. I mean, you don't have a lot of deserts in Sweden. So, yeah, I mean, and interactions with people are also, of course, completely different here. I mean, you can I mean, in Sweden and in the Nordics in general, people are quite reserved. They form tight circles around themselves and rarely burst that little bubble. Here you can be, randomly invited for lunch by a stranger just because, you look a little bit foreign and they are interested. So it's in that sense also very different. But everything has its pluses and minuses.
Yeah. Coming back to this, you said you're 22 when you finished your bachelor's and master's in engineering physics and moved to
Yes.
Sweden.
Well, no, that was a somewhat a simplification. So
Okay.
so first of all, my bachelor program in Russia was 4 years. That's
Okay.
one sort of peculiarity. So the whole program, bachelor plus master, was 6 years. And I left in the middle of the master. So I left after the 5th year. And then the last year, I sort of did two universities in parallel, essentially, which was more or less possible because most of the work was, thesis work. So essentially, I mean, the difficult part was that I did 2 separate master theses. One was at a company and one was, my own finite difference Fortran code. So this is very different. But also what helped is that in the Russian program, you work on your thesis throughout the whole 2 years. So it's not like in Sweden, it was just, half a year, you do nothing, only the thesis. In Russia, that was not the case. So you sort of start working. So I already had stuff done by the time I was having this overlap.
Okay, cool. So, and maybe this gets at the next question. Can you describe your first experience with simulation? What was it? Where did it happen?
So I guess, well, in a rudimental sense, it was at the computational physics course back in Moscow, which was, I think, on my 4th year. And that one started, with the basics, Lagrange interpolation, trapezoidal rule for integration, all of that stuff. Then eventually to ODEs and things like that. I don't think we ever made it to PDEs in that course, but that was probably the first experience. And I liked it because I always liked programming. As a matter of fact, the fact that I started in this engineering physics program was kind of a coincidence. I wanted to go for the IT program, but for that you needed the best the best grade at the entrance exam, and I didn't get the best grade. So I got just enough to enter the physics program. So that was a coincidence, but that just goes to show that I was always a little bit interested in programming, and that was obviously some kind of combination of physics, math, and programming. So it had its appeal. So eventually, when it was time to pick up the bachelor thesis, that's sort of a direction I was looking at, and that was probably sort of a real first experience was the bachelor thesis, which was 1D Fortran, but it was PDEs and it was combustion in porous media actually. I mean, I didn't start everything from scratch.
Can you give an application of combustion in porous media? I'm not a combustion person, so combustion in porous media just sounds very foreign to me, but what applications would that be?
Yeah, that's a good question. At this point, I am struggling to answer that as well. I remember that the whole gist of it was that somehow one can stabilize this flame front where you want it, and but there was all very. I mean, I think I have obviously mentioned some applications in the introduction to my thesis, but by this time I forgot it.
We'll just have to go find it. That's fine.
So yeah, I don't think I can give a very good answer at this point. Yeah, it's been some time.
Oh, that's fine. I was just curious. So that's cool. So one other question on this too. I think I came from a background of like seeing a terminal command line just like terrified me. And I can't give you a reason why. Like it was not something that I was exposed to early on. And so I've always had like this feeling in the back of my mind of like, at least especially in undergrad, after I got into grad school, I had to get over the programming hurdle, right? You just have to program. But what advice would you give to people who maybe are in similar shoes as I was in, that they're not as familiar with programming? And what do you think are some common misconceptions people have with it? Maybe a terminal's intimidating, or jumping into OpenFOAM for their first time, or any open source software that really is more of a Linux setup, command line setup, terminal setup. What would you give them?
Right. Well, I mean, probably the first thing to say is that programming and command line are not necessarily have to, be together, right? You can do a lot of programming without having a command line. You can use
Yes.
a good IDE, and you'll be perfectly fine. So I think for programming, there's a lot of, I mean, it's an amazing time to learn programming because you have so much, courses and tutorials and, from YouTube to dedicated platforms, which will even have a little IDE for you in the website where you can, punch things in. So I think it's just, Google and start with something, probably with Python because it's pretty easy. And once you get into that, you can, sort of expand wherever you feel necessary, really. With the command line, I don't know. I guess you just got to bite the bullet. I mean, yeah, there's not much you can do, right? I mean, it's you just have to overcome the fear and start with simple things like just moving around the directory tree and copying and moving and listing and things like that. Then probably eventually you should learn how to use some editor for files which can be used inside a terminal. And essentially, I guess there's two big options, which is Emacs and Vim, right? But there's also Nano, and I mean, there's a bunch of others. I would say maybe learning very, very rudimentary Vim could be good because it's installed everywhere by default. So if you know, at least how to open a file, edit it a bit, and save it and quit, which seems to be the biggest issue, right? That's a meme. Then you're kind of already in good shape, I would say. But yeah, I don't know. I mean, it's for me, the command line started back when I was a child, and there was no Linux at the time. But at some point, your Windows machine would get to such a disgusting state that you need to boot up the DOS command line, write format C, and then reinstall everything. And I don't know, maybe around when I was, 12 or something, I sort of learned how to do that from my brother. I have a 4-year older brother who is now he's a software developer, so he's always been an IT guy.
Yeah.
So that was sort of when you got to learn not to fear it too much. But yeah, that was also very rudimentary. I mean, just also change directory, list directory, format C.
That's awesome. Awesome advice and awesome experiences. And yeah, I wished I would have learned sooner and bit the bullet sooner. So I actually just installed Linux on my machine the other day, and that was the first time I'd set it up and done it myself. In grad school, I'd had someone help me, but I felt so good after it. I just felt like, yes, I did this. So it's good stuff. Okay, how did you worked at Alton in Sweden?
Yeah.
And what lessons did you learn there, right? Most of your career has been in research side, academia. But what did that experience at Alton do for you in your career?
Yeah. So I started there as a master thesis student. And there was, all of the standard CFD tools. So I think it gave me an understanding in terms of what tooling is used. So we used Fluent. We used ANSYS Mechanical because it was an FSI thesis. And we used ANSA for the meshing. And yeah, so I mean, the end I became pretty good at those. It was a consultancy, so it was pretty high-paced projects. Sometimes, just 1-2 weeks, you start from the CAD and then you have to make a PowerPoint. Very different clients also. Some people just didn't know what CFD was, that kind of level. And then some people were essentially experts in CFD who are sort of outsourcing a bit of CFD work in their company to an external partner. Yeah, I think I got the sort of a hand of what happens inside a sort of a company maybe which is not super specialized, right? So this is probably very different from the CFD which you get, I don't know, at Boeing or something, or like at Volvo, where you more or less do the same type of flows, right? You have probably quite a bit of your own tools. You probably have a very streamlined pipeline. I assume. But I mean, since you're working on the same stuff for at least decades in terms of CFD, probably there's some things which are set up and very rigorous. So I did not experience much of that. So it was the other side of a coin where you sort of just get a project with a completely new physics, completely new geometry, and you try to just pull something out, perhaps overselling a little bit what you can do in 2 weeks, right? If we're being honest. But it's all, I mean, in the end, with those initial projects, you sort of try to hook the client, give them a little bit of, idea what we can do, and hopefully then it expanded into some bigger thing, which then it can be done more rigorously with more tests, more, methodology, experimentation, and things like that. So yeah, I think I also got a glimpse of what complex geometry is. People like to talk about complex geometry, and what people mean by complex geometry is very, very different depending on who you ask. Like, so in academia, it can mean, I don't know, an airfoil can be a complex geometry if you go to the extreme. Anything which is not a box is complex geometry.
Not a cylinder and not a box.
Yeah. So I mean, I'm joking a little bit, but not too much. Whereas in industry, sometimes you get such a nasty thing. I mean, it's really horror. I mean, you have to clean it up and all of that stuff. And so, in that sense, I'm glad to have experienced that end of complexity. So it's that I think was very good for me.
Yeah. Was transition, so your master's was part of this project, right? Or maybe describe that relationship again. Like, you did your master's thesis with that company and you were doing consulting jobs on the side as part of your work at that company, or?
No. So so my master thesis was essentially a consulting project framed as a master thesis. So it was another company called FMC in Norway, for whom we were doing the project via the consulting company. And then after I finished that, I got an employment there and stayed for about a year.
Okay. So why did you return for a PhD? Was that something that you wanted to do? Is it something that was just, you just felt like, I want to go back, I miss it? Or
Yeah, I mean, somehow that was always the intention in some sense. I always wanted to do it. There may be some family legacy which influenced me. Both my parents are scientists. Both my grandfathers have PhDs. So it sort of runs in the family.
Deep roots.
Yeah. And my brother didn't do it, so I thought, well, it's up to me then. No, I mean, it's not really like that. But it certainly had its influence, I'm sure. And I did want to do a PhD, but you know how it works in academia. I mean, you have to be a little bit lucky if you want to be at a particular place that there's money and people who want to hire you. As it happens, there were actually people at Chalmers, one professor, which wanted to work with me, but the material part of the story didn't add up. So eventually I started searching outside, and I was quite lucky to have found something in Sweden pretty quick.
Yeah, that's awesome. Glad it worked out. So what are some common misconceptions? Well, so you said a lot of wall-modeled LES in your PhD, right? What are some common misconceptions people have about wall-modeled LES?
Yeah, good question. It's a very niche thing still, so I don't know if there's a lot of people that have any kind of conception but I would say maybe one misconception is that it is a cheap method. I mean, because that's sort of how it's sold, right? That you have LES, it's very expensive, so we can make it cheaper by using wall modeling. And that is true, but it's cheaper with respect to the well-resolved LES, not with respect to, RANS or something, or even DES. It is still a very expensive approach. So that's a reason why if you look at, the papers where they try to apply it to, like the NASA CRM, that's kind of a fuselage with a wing type of thing, you still cannot really do that flow with well-modeled LES by actually applying it with, according to all the rules, so to speak. So usually people focus on just the wing, for example, which of course makes sense. It's the more interesting part. But yeah, it is probably a misconception that it can be very cheap. Yeah, otherwise, I'm not so sure. As I said, it's still a very niche approach.
Yeah.
I think there's a lot of maybe a little bit misunderstanding how you should mesh the boundary layer. For example, you don't necessarily have to refine the mesh towards the wall, which is very difficult for people to accept because that's like the first thing you learn about meshing boundary layers, that you have to refine towards the wall. But in wall model, yes, you don't necessarily have to do that, I would say. You can, but it's if you don't, it's still fine.
Yeah. So when maybe for someone who's new to this, like you said, they might not have any conception of wall modeled LES. Could you just give a hierarchy of going from RANs to DES, wall modeled LES, DNS? Like, are there maybe for some people who might not understand where that line transitions from DES to wall modeled LES to LES? And
Yeah. So I think this one has to start with the concept of turbulence modeling. And this, I think, is a term which is maybe not so well chosen because I think that one leads to a lot of misconceptions. Because if we start from the top with a DNS, we are solving Navier-Stokes equations and we are, resolving all the turbulence. And in general, I mean, one can, if you're outside this community, one could perhaps still see this as turbulence modeling because you are, simulating a turbulent flow. You're modeling it on the computer, but that's not what it means. So if you are resolving the scales, you're not doing turbulence modeling. So it's this particular thing it refers to. This kind of dichotomy between resolving the scales with your grid or having a model to sort of account for their effect. So if we look at that from that perspective, essentially this hierarchy which you named goes from resolving everything at DNS level towards resolving nothing and modeling everything at RANS level, right? So those are the two extremes. And then if we go to sort of intermediate steps, the focus, maybe we should, let's start from the top again. So if you do LES, then usually what you say is you spatially filter the solution somehow. So that you only look at the large scales, although that again is not a very good term. What you really want to say is you're looking at the energetic scales. And the reason why one should sort of point that out is because the whole problem with LES starts in the boundary layer when it comes to cost. And the eddies in the boundary layer are small, but you still have to resolve them because they're energetic. So there this large becomes, you have the peak in turbulence kinetic energy at y plus 12 or something, and you have to resolve that in an LES, even though it's large eddy simulation. So that's a little bit tricky. And as I said, with LES, the boundary layers really are the problem because if you go to high Reynolds numbers, then you have to throw pretty much all your grid in this tiny, tiny, tiny little thin layer right close to the wall. So essentially this forbids simulating most industrially relevant flows. However, this of course has been recognized, and two ways of sort of alleviating this issue have been put forward. If we start from DES, which was introduced by Spillard and colleagues, I think in 1997, the idea is that you take the whole boundary layer and you treat it with RANs. Okay, so the whole boundary layer. And then you sort of try to realize when you are in the boundary layer and when you're not. For example, when are you separating? I think the original paper had the backward-facing step as an example. And you have, of course, all these issues with determining where should the LES kick in and so on. It's called the gray area problem, gray zone. And there's a lot of advancements which essentially work on that. For example, DDES is just, sort of essentially an upgrade to try to fix that in a better way. Now, if we go to wall modeled LES, then we still fully resolve most of the boundary layer. And here one needs to know a little bit of boundary layer theory to understand what I'm talking about, because the boundary layer itself is split into several, well, let's call it sublayers or regions. And it's this particular small part of the boundary layer, which is called the inner layer, which is right close to the wall, which is causing most of the problems, so to speak. And in wall model LES, we try to introduce a model just for that small region. Okay, so if applied sort of in a canonical way, DES is cheaper, much cheaper, because you treat the whole boundary layer as RANS. In the wall model LES, only a very small portion of it. I guess that's pretty much it.
Yeah, no, very, very clear and sequential breakdown. Thank you. Thank you for that. So tell me now about Eddylicious and what Eddylicious does.
Well, so Eddylicious essentially came, it came from an idea of trying to have a Python library where we could implement different inflow generation methods. And to give a background here, when you do LES and you have an inlet, you have a huge problem, because of course in LES or DNS or in any method where you resolve scales, at the inlet you should also give a scale resolved field, right? So you should have all the vortices and stuff which are coming from somewhere upstream entering your domain. And the question is, how do you generate them, right? And of course, there's a whole body of literature with various approaches. Some are essentially based on, statistics and this type of signal processing to sort of given, for example, the mean velocity profile and the, mean variances of a velocity field, generate these instantaneous eddies somehow. And there are other approaches. So that's the problem sort of which one is trying to solve. And then I thought, okay, maybe we could, try to have a Python library where we would have many of these methods so we could easily compare, which would act as some kind of intermediary that you generate the methods, you save them to essentially just to some file. And then in your CFD code, you should just be able to read boundary data from that file. And in this way, we could provide, an array of methods to different codes. Because right now, usually what happens is you have different methods spread out across different CFD codes. Now, unfortunately, that dream did not come true. So Eddylicious has not been worked on since maybe 2017 or so. I implemented my method, and probably the implementation is, the structure of that package should also be reworked. And I still wish maybe that somehow, I think the idea is still good in terms of having that package. It would be fun to have it and to have reference implementations for different methods in the literature. But somehow maybe I need to reinvigorate that and start contacting people somehow, probably after having reworked the code a little bit. So if anyone is interested, feel free to contact me either on GitHub or just directly. Somehow, it gets forked once in a while, and so people somehow arrive to the web page still, and so I think it has some relevance still. But unfortunately, it's sort of still in its infancy.
Yeah, I'll have to. A colleague of mine, friend of mine, have a community on School, and it's a platform where we'll have to put it there. There's a lot of people that want to work on projects, CFD projects, so that'll be something we can do, is dump it there and see if people are interested in helping you out or adding some code to it. So awesome. Let's jump to Turbulucid. Did I get that one right?
Yeah. So that one is a completely different thing. So that one is the visualization package. And essentially, it deals with the following problem: that you have some kind of 2D data living on an unstructured mesh. So in my case, the 2D data usually comes from averaging along one direction of the statistical fields, because in many canonical turbulent flows, you have one direction usually the spanwise direction, which is sort of statistically homogeneous. So if you're doing an LES, then at the end of your simulation, you can just average across that direction to essentially improve the quality of your statistics. A lot of flows are like that, starting from, canonical flat plate boundary layers, eddy airfoil, right? You just pick a thickness, and then set periodic boundary conditions in the span. Other alternatives is that if you have a truly 3D field, but then you just do a slice in ParaView and save that slice, that also gives you an unstructured 2D field. And what I wanted to do, of course, is some plots for my papers where I would have a 2D field living on this unstructured grid. And I wanted to do, the stuff you can do in, let's say, Matplotlib and, those Python packages where you can, set exactly the title and, the font and it's rendered in LaTeX and it looks nice and so on and so forth. So essentially, the package is a glue between VTK, which is a backbone of ParaView, if some of you are using it, and Matplotlib, which is the most popular visualization package in Python. So it loads the data using VTK. It has some we can call them filters. It's essentially what VTK uses as a name for some kind of way of, processing your data. For example, extracting a line profile out of the 2D data. So that is all done in VTK, and then the data which is returned can be used in Matplotlib to plot. And there are some wrapper functions which allow you to, for example, just plot the 2D field or plot some vectors and stuff like that. And that package is still sort of in a state which is completely usable. Of course, more things could be added on demand, so to speak, by people who need it, if they have the energy. But it does do the basics, and I think it's still very useful.
Yeah. And what was the genesis for both of these tools? Was it just a problem that you had in your own research that you wanted to address?
Yeah, absolutely. So all of this was essentially something which we're doing in my research. And exactly as you say, I end up with a problem. I need to visualize this thing. And since I liked software development, it's I prefer to, spend the time to learn how to actually write a Python package and do things a little bit more properly.
Yeah, that's neat. I was just reading a paper recently. It was by Richard Hamming, and he was talking about this very concept. He said that there's so many times that if you just take the effort to abstract something and to get the process down, that it pays dividends in your career later, right? Like he got to the point where he was at Bell Labs that he said, I can't solve all these problems. I need to solve one problem once and generalize it and then move on. And he just talked about the importance of that. And that really stood out to me as he said, he described that, just that benefit of retaining it and then having that tool moving forward. Yeah. So that's awesome. So you taught scientific computing for a while, right?
Yeah, 5 years essentially.
What benefits came to you from that as a byproduct of teaching? Did you feel ready and prepared to teach scientific computing, or was it assigned to you, or how did that even come about that you were teaching it?
Well, it came about because I speak Swedish.
Okay.
So by the time, the problem at Swedish universities is that, of course, you have these huge bachelor level courses taken by hundreds of students, which have to be taught in Swedish. Whereas the personnel, if you look at, in principle, all faculty should speak Swedish. That's somehow the condition that when you're hired as assistant professor, you sort of make a pledge that within the 4 years or 5 years, whatever, until you get tenure, you will be able to teach in Swedish. And people try to fulfill that with various degree of success. But then if you look at postdocs and PhD students, then of course, well, depending on where you are, but usually most of them don't speak Swedish because they are from abroad. So that means that if you do speak Swedish, probably you'll be assigned a bachelor course, which to some degree is a little bit unfair. You're kind of, it depends, but one could argue that, having a master course in your CV is somehow better, although I don't know if that's necessarily true. But yeah, it is what it is, so to speak. So then I was assigned this scientific computing course, which is actually given to, I think, all engineering students in Uppsala. So it's a huge course, and we're several TAs on that course. So yeah, that's how I ended up there. And was I ready? I would say pretty much, because it was very similar to that course, which, I told that started my journey, so to speak. So I
Yeah.
think it was, numerical integration, Newton's method for nonlinear algebraic equations. I think the most difficult part was LU factorization, which I think most of the students didn't like so much, and maybe not us either. Yeah, so I think it was also complicated by the fact that most people had zero programming background. So the
Okay.
beginning of the course was actually a lot about learning, how to do some MATLAB for the students. What is a loop? Realize that a script will, execute sequentially and not, just jump around. Very basic stuff. And that was actually very rewarding to teach people from complete scratch, because they go from absolute zero, just knowing nothing, to,
Yeah.
knowing something. I mean, they weren't extremely good programmers by the end of that short course, but they could do some things, and some people liked it, and so on and so forth. So in that sense, it was actually quite rewarding. And I actually, yeah, I from that perspective, like teaching basic courses. I think you really get a lot of these aha moments from people, which you don't get so much, I think, in an advanced course.
Yeah. Yeah. That's really neat. So, can you tell me about the development of your LES VOF methodology for the multi-phase stuff you did?
Yes, sure. I mean, we didn't do that much methodology development on on the level of numerics, so to speak. We took the stuff which was in OpenFOAM, and by that time the LES part was, to me, quite familiar, because this was during my first postdoc. And for the VOF, we tested the different methods which were there. One is this isoid vector, which is a geometric VOF. And the other one is this algebraic VOF called Mules, or Mules. I don't really know how to pronounce it properly. And we tested them both on hydraulic jump, which was at the time still one of the first, scale resolving hydraulic jump simulations. There's been one DNS done, and I think maybe one or two other LES. So that was relatively new. But then in parallel, we've been applying it to this nice marine technology problem. It's actually a pretty neat idea. It's called air lubrication. And the idea is that you sort of try to have a kind of a layer of air under your hull so that you reduce the friction. And you can do it in various ways. You can, for example, just introduce a swarm of bubbles, like a huge swarm, and that's the one which is most used commercially. But then what we were studying was called like an internal cavity. So you have like a small cavity in the hull, in which you try to keep the air as you go. And we were basically studying the dynamics of water-air interaction in that cavity, because what you want to avoid is the air to leak. Because if the air leaks, you have to pump in new air, and then this whole energy trade-off might be a little bit shaky in terms of how much you save due to friction and how much you lose for keeping the whole system running.
Injecting.
And the study basically focuses on that so-called closure region in the end of the cavity where most of the leakage seems to happen usually. So that's probably the most applied research I've done, I would say. It was still it was not a real hull. It was a copy of an experimental facility which was also used to study this. But still, the problem was in its nature quite applied. But yes, it was, of course, when you go multi-phase, there's a lot of issues with stability and all of those things which you don't really experience, because you have this ratio of densities of 1,000 between, air and water. in a lot of papers, if you look closely, they, for example, say, well, we are going, in our paper, we model air as 10 times more dense than it is physically, because then we can keep a simulation stable. So people do various funny tricks because it's actually difficult. I mean, to have this very strong material property jump. But yeah, when it works, you get some very nice videos. So it's all worth it.
It's awesome. You'll have to give us a link to some of those videos. So I'm completely new to that. Is that like industry standard now to have bubble swarms for large transport ships, or is it?
Nah, industry standard is probably a stretch, but there are vessels in operations which use that. And I believe now
Okay.
there's even a vessel which uses the cavity. What you do is you kind of have a bunch of cavities, kind of
Okay.
stacked one behind the other, because a very big one would be very difficult to keep alive. But so that you have several of them. Yeah. So yeah, it's
That's
used.
neat.
It's used.
Yeah, that's really neat. I did not realize that. Okay, let's transition to some more DNS spectral methods. So NEC 5000, what's been your experience with NEC 5000? And again, what do you think are misconceptions people have about high order methods?
Right. Well, let's start. So you said spectral. We should say spectral element. So
Yes.
that's because there's a difference. When one says spectral, one usually means that you have essentially a global, a global spectral basis in one of your, at least in one of your dimensions. For example, in X or in X and Z. Very common is that you have X and Z, so span-wise and stream-wise, you have some kind of Fourier thing, and then in the whole normal direction, you, for example, use finite differences, which are second order. For example, it's not so uncommon. For example, in the atmospheric community, for atmospheric boundary layers, but various combinations exist. But when we talk about the spectral element method, it is essentially a high order finite element method. So you have a mesh, right? It can be unstructured. Depending on the code, various restrictions can be on the shape. In NEC 5000, you only have hexahedrals. For example, in Nectar++, I think you also have tetrahedrals. In NECO, so far only hexahedrals as well. So there's a difference there. But it is essentially, as I said, it's a high order finite element method with some particular choices, technicalities, which is we should probably not delve into here regarding the choice of the how you locate the nodes in each element and so on and so forth. So maybe one misconception is that SEM is a spectral. I mean, it's sort of spectral within an element, right? So if you increase the polynomial order, the convergence will be spectral. Yes. Misconceptions. I don't know. Maybe I think a misconception is that if you have a high order method, then for any given mesh, you necessarily get a better result. Which is, I mean, not really true, right? We have to keep in mind that the order of accuracy is an asymptotic property, right? So what it says is that when your, whatever time step, or if it's a high order in time, or your mesh size, as it goes to 0, the error will go down as the mesh size to the power p, where p, everyone has his own boundaries. So what is high order? Well, I would say at least 3, right? But that's again, that's an asymptotic property, right? So that's important to keep in mind, and that's why, for example, in the LES community, there's still quite a bit of arguments, so to speak, whether you should do high order or not, whether there's any big benefit, because by design you are never in the asymptotic regime, because the asymptotic regime is DNS. Right, so there are these. This is an important issue, actually, an important practical issue. So one has to keep that in mind. That being said, there's quite a bit of evidence that for LES, still high order methods give you a benefit. But, it's always a trade-off because there are restrictions, for example, as I said, in the shapes of your elements, right? For example, in OpenFOAM or in Fluent, you can have just arbitrary polyhedra, right? You cannot have that with a spectral element method. Robustness is an issue. Behavior and course meshes is an issue. So I think there's, for example, in OpenFOAM, there has been some sort of attempts at developing a DG solver within OpenFOAM. And I'm not sure what the status of that is. It has stagnated a little bit, I think. But I remember at the time, I think a lot of people thought that, well, we'll just upgrade to that, and everything, with no change, just everything will just become more accurate. And it's not quite that easy. Because a lot of things change, not just the order of accuracy. Once you switch numerical methodology completely, right? So even though DG can be seen as somehow a natural extension of finite volumes into the higher order method space, still it will bring its own difficulties. It's not just that you upgrade what you have to something better with no minuses.
There's always trade-offs, huh? Yeah. What are the limitations? So background here, I took an advanced CFD class in my PhD, and we talked about high order methods. We were going to spend a lot more time on it, but it was professor's first time teaching the course, and they'd let some people into the course that had never had a CFD course. So we spent a lot of time rehashing things. But one of the things that I do remember talking about was some of the limitations on boundary conditions. And maybe my memory has not served me well, and maybe it was just specific to NEC 5000. But it felt like there were some limitations on the problems that you could solve with NEC 5000.
In terms of boundary conditions.
In terms of boundary conditions.
Yes, so now I have to be careful not to say something which is not true. I believe that some boundary conditions in NEC 5000 are forced to be kind of axis aligned. So your boundary has to be aligned with an axis.
Okay.
With a Cartesian coordinate. I think the symmetry condition is like that. And perhaps something else. Now, whether that is a completely fundamental property of a numerical method, I do not dare say. Or whether that can actually be, it was just perhaps never implemented because in 99% of the time, your symmetry plane is in fact aligned with a coordinate axis. So, but generally, of course, the boundaries are always where things get messed up, right? Because somehow if you think of finite differences, you usually rely on some stencil, right? And if you go towards the boundary, suddenly, towards the boundary, there's no more nodes. So you have to either switch stencil to a one-sided, or you have to, and I'm not saying that's some kind of severe limitation in that sense, but you certainly have to do something to make it work. And how to apply the boundary conditions, whether, you strongly enforce them or you weakly enforce them, meaning that they will be fulfilled only, again, in the limit of your mesh size going to 0 and so on. There are a lot of subtleties like that and, a lot of research. And so, of course, boundaries are always where, things go bad.
It's always where things get interesting, huh? So you're involved with the turbulence model development with OpenFOAM. And how did you're the chair of, and how did that start, came about?
Yes. So I believe the whole thing started maybe 3 years ago. It was certainly during my first postdoc, which means it was between 2018 and 2020. So yeah, that means it's more than 3 years, isn't it? Time flies. Yes, so that's when the OpenFOAM.com version of OpenFOAM started this whole so-called governance project, which was essentially trying to form these committees based on either, scientific areas in some sense. We can call them, I don't know, numerical methods, turbulence modeling, or applications, for example, automotive or nuclear, marine, and so on. And I don't think there was an extremely clear idea of what exactly we were supposed to do. And at least from our perspective, it was very much up to us and to our first chair, Charlie Mukha, to sort of figure out what is it that we are actually supposed to be doing. Because I think there was this good thought of involving the community, because this has long been an issue with OpenFOAM, I would say, at least to some degree, that if you had something to contribute and you felt like this could be used by many people, it was not straightforward to sort of put it out there either into OpenFOAM itself or at least as some kind of plugin or something. I think that was the background thought, but the way everything was, the whole process was not really set up. So in the beginning, we thought that we would sort of analyze the contributions which could come in, and then if we say this is good, then they would be added to the code essentially. But that turned out to be not really a well-functioning model, because the barrier for the contribution to be good enough was very, very high from the perspective of the developers of the code at OpenCFD. Because, and it's understandable. I'm not saying this as a criticism, because of course, once they put in the code, they have to maintain it, right? They have to maintain it. They have to. So if that person, who contributed disappears at some point, quits academia or whatever, starts doing machine learning, then if nobody understands what that code actually does, then it's a huge problem for them, right? They probably have to remove it.
Yeah.
And maybe they already have some client which relies on it. So that was not quite the approach which was sort of working out well. So now what we transitioned to together with OpenCFD is that inside OpenFOAM there is a directory called modules, which is essentially where you can have external code. So it's simply essentially what is inside that directory is just links to repositories. And one of such submodules is curated by us, by the Turbulence committee. And this gives us the autonomy to, we don't have to ask anyone what we put in there. If we deem that this is good enough, we put it in. And we have, a set of criteria, which are very simple. Essentially, you should have a tutorial, you should have a README file, and the code should compile with the latest version. Yeah, this is somewhat, it's not very trivial, because, it's a big problem in the OpenFOAM community that the codes get updated, and then suddenly what you wrote maybe 5 years ago doesn't compile anymore. And that's one of the reasons why some people stay on a particular version, somehow forever, because they know that my code works here. Here I've tested stuff I'm not going to do the job of. So this was what we have to put this burden on people, because of course if we ship something with OpenFOAM, it has to compile with OpenFOAM, right? It's pretty obvious.
Yeah.
Yeah, but we additionally have simply a list of contributions which we call tier 0 contributions, for which there is essentially almost no requirements, just a tutorial, and that's it. Sorry, not tutorial, just a README, and that's it. And so it can be a complete work in progress, just a showcase. So this is what we're sort of heading with now, and we have, I think, 6 contributions there now, and we're trying to reach out to people to contribute their stuff. So consider this as being reached out to.
An invitation.
Dear listener and viewer. Yeah, so this is sort of what we're doing now. And then there's still some activities going on more formal interactions between us and OpenCFD in terms of us recommending what we really think should be added into the code, and we're still trying to develop how to fund those things and how these processes will work and how to iron that out. It's still not quite ironed out, but I still have my hopes high, and I think that this initiative has been good, even if not entirely thought through from the very beginning on how all the details. I should probably also mention how I ended up in the committee, because it was I was a postdoc at the time, and I simply mailed Charlie at that point and said I would like to be part of this. So, and after some time, he agreed to add me in. And then the thing is that the more senior you become, the less time you have. And on the committee, I'm more or less the least senior person. So that means that I ended up having most time, and therefore some of the initiatives which were performed by us in the end were sort of pushed and to some extent done by me. So that sort of put me in a position to become the chair, because people saw that, okay, I mean, he has the time and he's quite active, so it sort of got accepted that I'm a chair on the committee where we also have, Spalart and people which are much, much, much more, infinitely more senior than I am, so to speak. So initiative goes a long way. That's perhaps the point.
Yes. No, I love that. I love that you just took the initiative. I also had joined a committee that it was for civil engineers in the CFD committee there, and there was always this thought in the back of my mind, what am I doing here? Everybody else knows decades more than I do, but just getting in, that's how you learn, right? You just get in and go. So that's neat. That's really neat. Thanks for sharing. And I was smiling earlier, just coming back to the part of why certain people use a specific version of a code. Even on the commercial side, a lot of my peers in the industry will wait. They'll lag behind a release of the new code because there's always bugs in the new stuff, and they'll wait for those to get fixed. And so that was just something that was new to me, as I always wanted the newest version, but then someone a lot more senior to me said, hey, I think this will be helpful if you wait till the next release. Usually that's a more stable package with things worked out. Yeah. So anyway, it's just reminded me that it goes the same for commercial codes. So great discussion. One of the things I want to start to wrap up with is, to you, Timofey, what has been one of the coolest or most rewarding problems you've personally worked on with your career, whether it's CFD generally or Turbulence specifically, or maybe it's an academic problem or applied? What's been something that's really stood out to you that you've enjoyed and that was really rewarding?
Yeah, that's a very difficult question, of course. I think it's fair to say that I liked the software development part of a job quite a lot, right? I mean, there's a reason why I ended up doing all those codes and now participating with Netco, and it's somehow it's this act of creation, and then you run it and you get result. I think it's incredibly thrilling, and when you get some kind of nice video out of it, or I think that's probably, at least in the grand scheme of things, what I've found the most rewarding. It's not a particular problem as you framed it, but that's probably the process of my daily job which I enjoy most.
Yeah.
In terms of which problem was the most interesting, hard to say. I would say the coolest one was probably the marine one. Both because it was multi-phase and it was, it was a clear application which I could explain to pretty much everyone. When you work in, channel flow, which is a flow between two infinite parallel plates, the cell is significantly more difficult. Not to say that I don't like channel flows, although I probably ran too many channel flows in my life, but still. So maybe in terms of a problem, that was interesting. Although now I've sort of starting to like a little bit more of the mathy stuff as well, because I think with the
Ah,
high order methods, there is a huge, essentially open field of trying to make them more robust and, being able to live with coarser meshes and all of that stuff. I would like to go
yeah,
into that. I don't know if I have what it takes math-wise, but I would like to try.
that's cool. Well, I'm sure is one of the things that I have seen both in the literature that I read and in interviewing people is that curiosity and persistence, it can make up for a lot of brain horsepower someone might feel like they're lacking. And I personally feel that. Um, so I'd say go for it.
Yeah, yeah. One has to find
Yeah.
time. That's the most difficult thing, time.
That is the most
To be
difficult thing, right?
persistent, you have to have time.
Yep.
So
You
that's the
gotta
sort
have
of
the time.
the main.
Yeah. Yeah. So one more thing, a lot of listeners are just starting out in their career. This might be one of their first exposures to talking to a professional doing CFD. If you were to go back to Timofey 10, 15 years ago or when you started or your timeline, what advice would you have told your former self with what you know now?
Oh wow, yeah. I don't know. I mean, I have to admit that maybe if I went back 10 years and started over, I might have not done CFD. I don't know. It's one has to realize this is a niche thing. Even though it's growing, it is a niche thing. If you if you're good in something like optimization or statistics, you can still work in CFD, just not running the code. So but you can also work with a gazillion other things, right? So
Mhm.
of course it depends on preference, and I don't know what I would have said to myself. It's very, I mean, I don't have any regrets. Like if I had some obvious
No.
regrets, then I would probably, you know, go back to myself and try to avoid them. I'm still, of course, my main problem is that I'm still in the postdoc limbo, which has to end sooner than later in some way. And, whether I end up, thinking that I should go back and tell myself to quit after my PhD with academia and go to industry, that's a realistic scenario. But at the same time, I had a lot of very cool experiences, and now I'm in Saudi. Like, it's just I could never imagine I would be here of all places, and so it's very difficult to give advice. I guess one generic advice is while you have the time, like at university, try to learn the fundamentals. I think there's this kind of trade-off. People want to, for example, take a course where they would use Fluent so that when they apply for jobs, they can say, I know Fluent, which makes sense. But the thing is, it's easy to learn Fluent. That's what I mean. It's in the interest of ANSYS to make Fluent easy to learn because, they have a nice GUI. It's not difficult to learn Fluent. And I mean, when I was working as a CFD engineer, I mean, when I look back at what my knowledge was as a CFD engineer, I mean, man, I knew very, very, very little. So it's somehow goes to show that using software, I mean, most of us can learn. It's not a very big deal. Having time to learn, finite element method and sit and play with that is much, much more difficult. It's even much more difficult when you're in academia. It's infinitely probably more difficult if you're in industry, I suppose. So there are some things in life for which you only essentially have this time frame to do, and later it's not impossible, but it's difficult. So I would try to optimize working on those things when you are in that time frame. Yeah, I don't know.
That's that's awesome. One of I help a lot of people with resumes and preparing for jobs, and one of the things I've got my own meme I've created, and it's I can help you organize what you have better and clearer and present it well. but I can't serve a plate of filet mignon if you bring me the ingredients of a peanut butter and jelly sandwich, right? Like if you have experiences, and that's not a knock on anyone, right? That's just exactly what you were saying, that it's go deep, and you can always, yeah, you'll never regret going deep, and really getting the things that are hardest to acquire, and learning how to push buttons and where those buttons are is, like you said, so much easier than learning which button to push and why,
Yeah.
and what's happening because you pushed that button, correct? So
Yeah.
yeah, totally concur with that, Timofey. That's awesome advice, and best wishes to you and your future endeavors.
Yeah, same to you. Thanks a
And
lot for inviting me again. It was fun.
yeah, absolutely. Really enjoyed the discussion. And if people want to get in touch or collaborate with you, what's typically the best way to do that?
Yeah, I suppose you can message me on LinkedIn.
Okay.
Yeah, there's also my emails. I guess one can find them on Kaost website, I suppose. I haven't actually tried. I should maybe look if it's there.
Well, we'll put your LinkedIn profile in the show
Yeah.
notes for
That's
sure.
probably
So,
the best.
okay. Sounds good. Well, thank you.
Yeah, thank you.
Thank you for listening. Really, thank you. Did something about this episode stand out to you? If so, please go ahead and share it with others on LinkedIn or other social media so they can find this as well. See you next time.